attempt not to play any copyrighted music on the doorbell.
Right. Okay. So you're recording, Nathan.
Yep, we're all good.
Great. Well, so it all started uh, like this with a message from Ian saying he's planning on making a doorbell.
That's
Uh,
me. Hello.
that's Ian. Yeah. So and so I was like, yeah, well, that sounds interesting. Thinking it's going to be something that's like playing sound samples or stuff, but as she's talking about something that's actually going to make noise on tubular bells, I thought this sounds interesting with like an Arduino, and I reckon this was quite plausible, and actually I'd heard about this thing called TinyGo some time back, and I was like, this sounds a great opportunity. Okay, Ian, well, it sounds like the processor you've got automatic already is not TinyGo compatible, so I think you have to get another one so I can do the software in TinyGo. And so it started. Now, luckily, this happened when I just finished my last job, and I had a bit of a break where my wife Carmen was very happy that I would have lots of time to spend, doing stuff in the house, working in the garden. And then Ian comes along and gives me this really interesting project that I could spend lots of time on and spend time at the computer, even though I'm not actually working for 2.5 months. So there we go. So in this talk, I'm going to talk a little bit about choosing the device, and Ian's going to talk a bit about that, and some of the like I'm going to talk a little bit or quite a lot more about a driver that I wrote for it, which is like really simple but quite pleasingly simple, I'd say, and eventually trying to like play a tune on this thing. And at this point, I think it might be good to have Ian talk about his motivation and what he was thinking. Why did he ask me, and what and everything else about that. So I'm going to stop sharing my screen and let Ian talk.
Hi everyone. Quickly, a tiny bit of background to explain why I might be interested in musical doorbell. Myself and Roger are friends because we both have a passion for playing instrumental folk music. Roger's a keen violinist, and I play the guitar professionally, as well as some other instruments. And until recently, I toured the world playing music for a living as a professional folk musician. I also run a recording studio in the church, which I live next door to. And so I'm interested in technology, and I had recently had some success in listening to MIDI signals that were being sent out by my audio sequencer, and controlling an Arduino to turn on LED lights and to flash lights in time with metronomes, so that my client in the studio would know when the recording tracks were armed, when recording was taking place, and what the speed the metronome was going. So I'd already kind of been through and figured out inputs, how to use solid state relays to silently trigger both mains level inputs and DC voltages. And I also recently moved to Thropton, the same village that Roger recently moved to, and found myself with a big house with no doorbell. So I was looking online and remembering my grandmother's house, where there used to be, you would walk in, and instead of a small thing with little tiny bells inside, there was two very long brass tubes that with a solenoid between them that moves both directions. And it'd go like dong dong, and when you pushed the button, it would send the solenoid in one direction, and when you did it, it would do the opposite polarity, and it would ding it onto the other bell. So two tubes, and those are suspended from a box that hung on the wall. So I started looking online at eBay and things like that, and trying to figure out where you could buy like one of these vintage bells, because no one's made them since the 70s. because people don't generally want to feed 240 volts to a switch which is connected outside in the rain in the British climate that people go and touch with wet hands often. It's probably illegal. So it's really difficult to get hold of them. The solenoids go wrong all the time because the wires can overheat if people hold them down for too long. Them being a physical device and often made with plastic components, those components can shatter because of the movement of the things, and they can get heated up and go brittle. So I got to the point where, as well, at this point, it would be more satisfactory if I could just build a doorbell that went ding dong and replicated the functionality of those old machines with a nice, loud, physical bell. And then after a bit, I thought, well, why would I just have two bells? I could have 3 or 4, and then I could play a peal of bells like a church, ding dong, ding dong, ding dong, ding dong. And then I looked a bit deeper. I thought, oh well, if I had just these 3 more notes, then I can have, you know, I don't know, some national anthems or something. If friends come visiting from different countries, I could surprise them with the Danish national anthem. And then eventually I realised that with 1.5 fully chromatic octaves, I could play Darth Vader's Imperial March, which became the kind of the standard for being able to play something that would amuse almost anybody on pressing the doorbell. So I contacted Roger because I'd already ordered a whole load of solenoids. Solenoid is a, where is it? Solenoid is a small electronic component. If you don't know that already, it's got a coil of wires in here. This is a 12-volt solenoid, and when you give it 12 volts through these wires, the magnetic current forces that to the other side, and when you take the power away, the spring here puts it back again. And what I discovered recently is that when the spring flings that back, that actually generates a voltage, an opposing voltage in the wires. So part of the circuitry I need to design needs to stop that generated voltage getting shoved in the wrong polarity back into the other components. So by the time I'd texted Roger to see if he could help me with the converting some sort of musical language into signals which would trigger the relays, which would then in turn turn on the 12 volts to the different solenoids, one for each note. I'd already got a plan to use Arduino because I know that it's a good device for it can natively recognize things like MIDI in the Arduino IDE, and I already knew how to make it recognize different button presses and some basic programming stuff, but nothing like in the league of what Roger is able to do. So, Roger, should I demonstrate and show one of the bells? You're muted, Rog.
Let's leave that till later.
Okay, I'll show you that later. But I'll show you one. Okay. So we are talking about, is that going to fall? No. We're talking about...
Spoiler, can you guess the musical doorbell does not actually work yet?
Yeah. So, but all the elements of it do. So this is a tube of aluminium, and I looked through all of the various different materials available for making a pleasing chime, and it turns out there's a lot more to it than just shorter one is a higher note and longer one is a longer note. That it doesn't have the same linear relationship that a guitar string would, where half the length is an octave higher. It's actually much more complex and to do with the mass of each section of the tube. It's also important that you attach the tube at the right spot, because through down the physical tube there's several nodes which are a point where the wave passes through zero in effect, and that node means that if you mount it there, then the mounting has no effect on the resonance and the sustain of the thing. So this one isn't very sustainful because it's quite thick for the note that we're after. But if I was to hold it in the wrong place, we get almost nothing, and then when I get closer to 22.6% down, the more I get closer to that, the longer it sustains for. So I went to the Newcastle Metal Supermarket, and a big, scary, gruff man there who didn't seem to speak in more than one syllable ever showed me to lots of different bits of aluminium tubing and brass tubing, and I dinged them all with my wooden mallet to find out the ideal ratio of price to sound quality, and ended up with aluminium, which is luckily also absolutely the cheapest. So the 18 to 22 of these tubes that we will need to have a musically useful range of notes. It costs something in the region of 180 to 200 pounds, so it's not a tiny amount of money to spend on a doorbell. And thus I want the functionality that Roger brings to the party to be something really special and unique that makes people want to come and press the doorbell button on my house. So there you go, Roger, over to you.
So I guess that was the brief. Let's go back to my slides, shall we? Okay. There we go. Yeah, so that was the brief. We wanted. Well, Ian hasn't talked at all about actually building the hardware. So he actually not only went and investigated all those bells, those bells and stuff, but he actually put the actual hardware together. So we chose between us a processor, one that would support TinyGo, and here is the actual board that Ian put together with beautifully wired, absolutely gorgeous soldering skills there, nice wiring skills.
We can't see it, Roger, can we? Are you showing us it on your camera?
Ah, shit. Okay, excuse me. Let me stop sharing, and then I can show you this, the actual device. Yes, and you can see the beautiful soldering skills there. Well, no, you can't actually see the soldering at all, but you can see the nice wiring skills. You can see it works in the studio. And yeah, I'll actually show you, like we've got 3 relay boards here. We've got this here and here, which basically those are, each one has 8 relays on. So we've got a total of 24 relays. That can be used to drive things, drive the actual bells. We've got a couple of displays here, 5 buttons. 5 is a bit overkill because I think he only has 2 doors in the house, but you know, you can never have too many buttons. And the actual chip itself is that's the Arduino. It's actually an itsy bitsy M4. And these chips I'll talk about in a moment.
Yeah.
So
I could explain just a tiny bit about some basics of the way that the circuit works. So it starts off with Roger deals with the inputs, and Roger will talk about we've got a special way of doing inputs and outputs into the itsy bitsy, because these tiny boards just don't have enough pins around the outside to have 20 something musical notes, each driving a voltage, and also the maximum amount of power that you can draw from something that gets its input voltage from a USB power supply is kind of limited, and can cause a voltage drop if you're driving several solenoids at once. So the solenoids are listening for a trigger voltage. They operate at 5 volts, so it means that the actual voltage that they're using to switch things on and off and to power the actual switch inside each solenoid, they've got their own separate power supply, which does not draw the current to do the switching work from the little microprocessor itself. So they're listening out for would you call it a digital input? So anything over 3.1 volts and it will switch the thing on, and anything less than that and it'll switch it off. So there you go.
Cool. Okay, so let me get back to my screen. Share screen. Okay. So we had this little issue that, so yeah, I suppose like first, like why did I actually want to do this in TinyGo? mainly because I like Go. I've done a lot in C in the past, and I'm over C. I don't really want to write this thing in C. I don't want to write it in Tiny Python. I'm not keen on Python really. And I thought I'd heard about TinyGo, and I really thought it would be nice to, to have a go at it, and maybe I can contribute something to, all the stuff around TinyGo. And one of the main motivations really is that I could see that we, this doorbell thing, we've got a few things going on. We've got buttons being pushed, we've got a tune being played, we've got several things happening at the same time. And I can do state machines, but state machines are really hard to reason about, I find, really hard to maintain. And I just want to write, if I play a tune, I want to just play the notes of the tune. I want to write a program that does that rather than deal with everything at once, which a state machine has to do. I'll talk a little bit about that later. For those of you unfamiliar with TinyGo, it's an entirely independent Go compiler. So normally, the Go project has a load of standard libraries which it does pull in, but all the compiler is based on LLVM. So it's basically a compiler that targets to LLVM, which is I can't remember even what it stands for, a virtual machine, and there's a big ecosystem around that which enables it to target all kinds of processors. And one of the really interesting things about it is that it has entirely separate runtime. So Go, the language, the standard language that we usually know as Go, is oriented towards server machines. It's oriented towards large machines with lots of RAM that need to run fast and can afford to expend lots of memory doing so. So it's very garbage collection oriented. It really needs at least 2 times as much memory as your working set to work properly. It allocates a lot. It's really, you can't run a Go program in less than, a few megabytes of memory, really, realistically. Whereas with these Arduino things, these little microprocessors, they might have 32K of RAM. This is something that the normal Go compiler cannot run in. And this is something that TinyGo really does well, and so it has an entirely separate runtime which gets rid of a lot of things. So it doesn't, for example, it doesn't scale to multiple processors particularly well, but that's not something you care about particularly on small processors. So that means you can pare things down a lot. It does some very interesting static analysis, so that instead of having global variables which are initialized when everything starts up, starting with 0 and initializing them, it actually enables them, if they're not changed, then it actually can put them in flash in read-only memory and thereby reduce the amount of memory resulting, which is pretty cool. And yeah, you can, so I heard about it from Ron Evans, who's the Mr. TinyGo, his talk at GoFCon 2019. And I'd been kind of looking for an opportunity to use it for a while. So this was a great opportunity. And as we said, we wanted, like, the initial thing was, oh yeah, we need one pin on the one GPIO, general purpose IO pin, for each of the outputs we're going to need. And we found this one, the Itsy M4, and it has 23 GPIO pins, which is actually just about sufficient. And that is actually the one we got. But then after Ian had ordered it, we realized, well, actually, we got I2C, I2C, that you can get these relatively cheap IO multiplexer devices once we've worked out the term to Google for. And then you can actually turn I2C is a 2-pin technology. So it's basically, you can use 2 pins and turn that into more or less as many as you like, as many outputs and inputs as you like. You won't be able to drive them as fast, but in this case, the solenoids need to be operated relatively slowly compared to computer speeds. So we found this device, which is pretty cheap, MCP 23017, which has 16 GPIO pins. So basically, if you've got one of these, you can drive 16 outputs or inputs. You can do both, and it costs. Actually, I think it's slightly more than $1. Yeah, I think you can get it for a couple of dollars, like just about £1. And it's got a really nice, simple API. And you look at the manual, it seems pretty plausible once you got your head around it. It turns out that. Well, I say no existing drivers in Go. Actually, there were some drivers. That's a lie. There are some drivers in Go, but they're not for TinyGo. There weren't any drivers for TinyGo, so I thought, okay, let's have a go at doing this. It looks pretty straightforward. So I'll talk a bit about the process of what the API looks like, and so it's quite nice because you involves kind of a bit twiddling is pretty fun, really. So you kind of start off. So I'm going to throw quite a lot of code over the wall here. Is there anyone that's not, apart from Ian, who's not familiar with Go here? So do I have to describe the syntax at all, or is everyone happy with what they see?
Oh, hello, Tommy.
Hey, me. But I mean, yeah. You don't like hold up the whole brigade for my benefit.
Well, I'll explain it a bit anyway. So
I should explain, Roger, that it's Tommy the accordion player who was at your fire pit that came to record.
Hey
and plays
Tommy,
the
how's it
accordion.
going? I'm sorry, I didn't recognize your name.
So I think
Fine.
he's motivated by finding out more. He's considering using small microprocessors for general musical purposes.
So you missed
Yeah.
all the useful part of the talk from you, Ian. There we go. So this is me talking about the software, and this is a bit of Go program. So here it's the very it's a low level thing. Actually, it's almost not worth doing this. So we've got this pins, which is a 16-bit integer, unsigned integer, which means that it's got it's 0 to 65,536. 35, and we're just pretending that it represents 16 pins. So here I've just included the body of this for just for example. So we want to get the pin number 0, pin from 0 to 16, and we'll just return this little Boolean expression to work out whether this particular bit is set or not, and similar stuff for set. And we've got convenience functions for high and for low to set pins to a particular thing. So this is almost not worth doing because you can just do this with just arithmetic. But it's a nice example of what you can make a little abstraction in Go that is actually very low cost, because the representation of pins is exactly one unsigned integer, 16-bit integer, and when you call get, for example, it's really no more overhead than if you hadn't had this object, this kind of abstraction with methods. So it's the method will be inlined. It's basically zero cost. So this is like kind of warm up for okay. So when you've got a pin, you want to be able to talk about, well, you've got its general purpose I/O. That means it can be input, it can be output. You need to be able to tell it what direction it is. So here's me describing what a pin can be. So it can either be input or it can be output. And the direction says it's one of these. It's either input or output, and you can configure it to be pull up to enable the pull up resistor, which means that in some circumstances you need that, and I can't quite remember why we needed it anyway.
Yeah, so that's because if you switches work by shorting one of your input pins to ground. And so the pull-up resistor pulls that back up to its voltage again. So you can do this externally by having a resistor and a switch. but most devices like Itsy Bitsys and Arduinos and things have got the pull-up resistors built in, so you just need to tell it to turn those on if you're using them.
Cool. So that's so this is another way you can configure the pin, and you can also say that when you set a 1 on this pin, it's going to turn it to when you make this pin high, it's actually going to be low on the output, and vice versa, which is kind of convenient because it means you don't have to worry. Like if Ian had said that, oh, I've changed this circuitry so that actually it's 0 to switch it on and 1 to switch it on, I can always just say, oh, high is on, and you can do that on a pin by pin basis. So here's the kind of overall thing for making a device. So for this is for the MCP, this driver that I did, and this is pretty standard stuff. I think for a driver, you give it this this so-called bus. I mean, we've only got one bus usually on a typical chip, but we provide there's the possibility of having more. And every I2C device has an address. So this is how we're going to talk to it. And when you've made this, you get a device and you can talk to it, and it's going to talk to one of the several. So in this case, we've got on this thing, we've got 3 of these chips. So we can divide, so we can drive actually 18, 16, 32, 48. We could actually drive 48 things. And we've got this set modes thing, which basically you have 1 pin mode for each of the pins, and that's how you configure the pins to be inputs or outputs or whatever we want. And if you want to set the outputs, then you'd call set, and if you want to get them, then so that you can see that we've got this pins which we defined earlier. So we're basically saying if we want to, we've got 16 pins, we're going to set all the pins to this thing, and we're also passing it a mask. So it's basically saying, let's set these pins to this value, but only if they're in this mask. So that means you can easily set, 1 or 2 of the pins and not all the others. You can just leave the others unchanged if you want, which is pretty useful. And you can get all the pins. One thing that I did do here, which is kind of useful. So what I wanted to be able to do is, like, for example, make it easy to configure all the pins to be one particular mode. And that's a bit awkward if you have to pass something where they're all the same. You've got 16 things of all the same value. So I said, if the very last value, if this is shorter than 16, then just replicate the very last one. So basically, if you pass it an array or a slice with 1 element in, then it'll basically configure it all to the last one. So if you pass it a slice with one value of output, then they'll all be configured to outputs, for example, which turns out to be quite nice actually, and I'll go into a bit more of that later. And there's also this convenience thing, which is you can get a pin value. You can ask for it, give me a pin value for this particular pin, for this particular number, and then you can access that independently. Actually, there's a get as well, of course. I haven't included that stupidly. So you can just call set or get on that, and it will just change that pin independently of the others. So that's quite useful so you can just pass that to something and it only knows about that one pin. That's actually exactly the same abstraction as there's this in the TinyGo standard library. There's a pin data type with exactly the same signature of set and get, and it's also got high and low. And because of the way that Go interfaces work, that means that actually you can have code that operates on one or the other without actually knowing whether it's talking to one of my MCP pins or whether it's talking to a hardware pin, which is also pretty nice. And one of the things I did, which none of the other drivers that I saw, I looked at a few of the other drivers for it. None of the others did this, but maybe they didn't have a need for quite so much I/O. like actually I've got all these three devices, and I really wanted to treat them individually. I didn't want to say, oh, if we're talking to device 0, then I just wanted to be able to talk to them as if it was one homogeneous thing. So I basically implemented a very similar interface on the same on the one level up. So okay, we've got pin slice, which is like any number of 16-bit things, of 16-bit values. So our pins before, this is actually any number of them. So if you had you could represent 32, so we've got 3 devices. That would be a pin slice with 3 elements in, and then you've got set and get methods for setting the individual bits within that. And it basically looks like the same sort of API again, and we can do the same thing with devices. So you put all the devices, as many as you like, into one thing, and it basically multiplexes them. So they're multiplexers, but in Go we sort of multiplex them up again, and then actually the API looks just the same, very similar. So when we've got set modes, well, okay, if you want to set them all to output mode, that's fine. You just provide a single element modes thing here. Or if you want to set pins, you can do pins and mask, just very similar. So if you want to have some of the thing crossing boundaries, that's no problem here. And the pin API works exactly the same, which is turns out pretty neat actually. I thought. Does anyone have any questions at all? I've been going fairly quickly, I think. Does that all make sense to everyone? Silence is good. Now, one of the interesting challenges here was testing it, because I like writing. When I write this code, I like to actually make sure that it works. But in this case, I think it's quite awkward. You can't run the Go testing infrastructure on one of these things. It's too heavyweight. But actually, there's not much about the code which makes it. I mean, apart from the fact that you actually need the device to make the output, you can actually test a lot of your expectations just by making a little faking up a little fake version of the I2C bus interface, and it's got a pretty small API actually. It turns out everything's done just through read register and write register. And so I thought, okay, that's easy. So instead of writing my code in terms inside in terms of the TinyGo standard type that it is, I just did it with an interface type, so I could implement it for my tests. And here's my a sort of sketch of my interface. You say, oh, okay, I want a bus, and then I can add a device here. And this, of course, is totally fake, but it's good enough that when the code calls read register, it'll say, oh, okay, we're getting it from this device, and it'll read whatever registers that you happen to have set up. So then, if you want to test a particular aspect of the code, you can set up the registers so that when it calls read, you just change them. When it calls read register, it'll return that value. So actually, this provided me quite a good way of wrote tests for the code, and quite good confidence that there were, because the actual API is pretty straightforward. The actual thing operated by the chip is pretty straightforward. I could actually write reasonably good tests for this. And actually, as it turned out, when I ran it on the actual thing, it all pretty much just worked first time, which was reasonably justification of the technique. And it's a good, it's nice. It actually means that technically you could use this driver by writing an adapter for this to some of the other I2C devices, say, that are available with the periph library, or some other libraries that run under, for example, on Raspberry Pis. you could actually use this driver to work on them too, which is kind of nice. So once we've got this driver, then we can we've checked that we can actually set the outputs and we can get values in. We get the buttons, and it turns out that the buttons, well, actually, they're really crap buttons. Ian knows they're crap buttons. They would probably cost about 20p each, and they're really noisy. I mean, all buttons are noisy, but these are really noisy. But anyway, so we want to. I thought I'd got rid of most of that code. In fact, I think if I no, damn it. Hold on, let me just. Excuse me. There, that's what it should have been. So we want to debounce it. It turns out there wasn't any out of the box debouncing functionality. I mean, it's kind of very easy to do. It's only 15 lines of code, but it's annoying to have to. I wanted to abstract it out, so this was my take on that. It's really simple. You basically say, this is the state I've seen most recently, and you ask it, is it stable? What's the stable state, and it'll tell you. That's really kind of simple, but that means that basically when you get if you get told that the button has changed, or maybe you're polling it, which we actually end up doing, you can just call update, and it'll give you the debounce state, which basically means that it's been in the same state for a certain length of time, something like 50 milliseconds in this case. So that's quite a kind of useful thing. So once we've got a debouncer, this is what our what the code for actually polling the buttons were. So technically you can get interrupts from these MCP 23L7 things, but I didn't get that far. And polling's pretty straightforward. It doesn't, we don't worry too much about using all the power. So it's just a loop, loops forever, and we've got a load of so we've actually got 5 buttons. So we've got a load of debouncers, one for each button. And this is pretty much the exact code. We've got a loop, and we get all the pins, and we go through debouncing the pins, and what's new state? Oh yes, so we've got this pins thing. This is just as introduced earlier. So basically, we're actually getting a stable state, and we're setting it in this new state. And if the state has changed, then we're going to send down a channel. Now this is something that Go gives you, which is really nice, I think, and was one of the main reasons that I wanted to do this thing in TinyGo. Gives you channels and Go routines. So this is an independent Go routine that is just sitting there, running, polling the pins, and every time it's changed, it's going to send this state down a channel, and then then it's going to wait. Then we're polling once a millisecond. Could be any time, or it could be interrupt driven. The point is, it doesn't matter. It's factored out into this nice independent piece of functionality where we've got this channel, which other things can now read on. Something else can read on, and to find out when the buttons when the buttons happened, without actually having to worry about polling or even how this is working, which is pretty cool, I think. So now we've got a channel that will tell us when things are so notice that we're using this pins type everywhere. Like this is just uint16, but we're using it to express what the current state of all the buttons all at the same time. So anytime any of the buttons change, we're going to get this thing that says this is what all the buttons look like right now. So to go back to, so that was all input side. To go back to kind of output side, like what does it mean to play a tune? Well, in this case, we've got these solenoids, and I thought that this is the, you know, sort of what's the simplest way that you can express a tune. You can't express a duration with these because it's not, you can't like say this bell is going to play for 5 seconds because actually there's nothing to stop it playing, and you can't hold the solenoid. You've got to strike it. So basically, it's like you just have like basically the input format for this is we're going to delay for some length of time, and then we're going to activate this channel. We're going to, so where a channel is one of the bells, and that I think, and it just have a list of those, and that I think is sufficient to do things like chords, because you just have a selection of like we'll delay for 0 length of time, activate this, you know, channel 1, channel 5, channel 8, and channel 10, and it will basically just do them all at once because it's not delaying between them. And then to actually make this into something that we're going to play, we basically work out, okay, so we want to activate this this solenoid for, we want to activate a solenoid. Basically, you raise the level up, and then leave it up for a certain number of times, say 50 milliseconds or some length of time, as yet to be determined, because we haven't actually hooked this thing up yet.
Roger, shall I very briefly demonstrate why that's important?
Yeah, do it. Why not?
Right,
Hold on.
so
I'll stop sharing, and then you can show me.
So here's a small bit of tube. This would be better with a longer tube. I'll take the other one. Okay, here we have an aluminium tube. So when you ding it, it makes a noise. And what you do when you ding on a bell with a mallet or with your hand is your hand bounces away. That's the natural human movement. But the solenoid just doesn't work in that way. A solenoid will apply a force to the central shaft when a voltage is applied. So if you apply a voltage for a very short amount of time, it won't have reached the point where it is in contact with the bell. It'll have got that far, and if you release it too early, it will get sprung back by the spring again. So there's the amount of, it's actually the amount of time is how long it takes the solenoid, when applied with 12 volts of voltage, to reach the end, and then you want to release it so that it isn't sat against the bell. Because if I was to ding this with my hand, but hold my hand against it, it immediately stops the sound again. What you need is the shortest possible moment of contact with enough power. And the solenoid also has to travel past the point at which it's just touching it to actually physically move the bell to one side. So that the length of time that what you would call a note, the length of time is the physical time that it takes in milliseconds for the voltage to get that all the way to the bell, and then turn it off at exactly the right moment, that it doesn't then stop the note at the same time. So this is why I told Roger that has to be a variable we can adjust so that we can get the best possible sustain. Okay.
So basically, we've got this input, which is like, okay, we're gonna play a note here, and then we're gonna play a note here, gonna play a note here, and then in order to work out what the actual set of actions we're going to do is, you, for each time you for each activation, you just add 2 events, one of which is on and the other is off, 50 milliseconds or however many milliseconds after that, you know, that duration after that event, and then you sort it all by time. And that means that you can get several on at the same time, but you just have to, once you've sorted it, you just have to go through that and play through those actions. So we have this, so I've got this nice independent thing which says, And this is how it looks in the code. Now I can't remember what this actually means. Basically, we're playing this action, and we've got the stop thing because actually we want if somebody presses a button, a doorbell, while the tune is being playing, we want it to stop playing the tune. And I can't remember why I've got the pins argument there. Well, you can see, but this is essentially. Yeah, no, this is because these pins are actually what we're going to play the tune on. So this is the slice of pin objects that we're actually going to set high or low depending on what we're doing in the tune. So this is actually all we need to play a tune. So we start now. We go through the sequence of actions where an action is a channel that we're going to activate, one of the bells, whether it's on or off, and when we're going to do this. So basically, we go through the sequence. We wait until it's time for that action, and if there's some time to wait, then we wait for it to happen, or for us to be stopped, and then we just set the pins to on or off. That's simple as that. Basically, we go through the tune, and when we're finished, we're done. Does that make sense to everyone? So it's actually slightly more complex than that. But for the purposes thing, because actually, if you're aborted, you actually want to just turn off all the things that you've just turned on. So because you don't want to leave them on because you've stopped playing the tune. But that it's not much more code. Yeah, and it says actual code deactivates all the active relays there. And timer is an interesting thing. So this is another place where TinyGo, slightly missing functionality in that this timer thing, I wanted to wait for either a time to happen or us to be stopped. And actually, there's no timer support. I mean, you can sleep, but there's no timer that sends on a channel support in TinyGo. So I implemented one, which is kind of fun because there's slightly different from the usual Go timer stuff. Because the usual Go timer stuff, you create a timer or reset every time you want to get a new event. Whereas this is slightly different functionality. Or slightly different trade-offs, and I took the opportunity to redesign it a little bit to make it slightly easier to use. And basically, it's designed for use by a single Go routine, and you can just say after this duration, it'll actually always return you the same struct. And when you reset, it ensures that you will never receive another another value on C, which is something that the standard Go timer suffers from somewhat. And you can stop it, and you have to close it at the end because there's actually potentially some Go routines in the background actually doing the sleeping for you. But that I might propose that for TinyGo. It might possibly, you never know, somebody might like it. So the top level loop I haven't really included here, and this was because it's a bit more involved, but it's really fairly straightforward. We wait for a button to be pushed by waiting on that button channel, and then we'll start play. We'll make a ding, and that's actually just amounts to doing play with a single note. So ding, and when we release, it goes dong. Or if you press it for quite a long time, then it'll play a random tune. That's the idea. And if you press it again while it's playing the tune, then it'll choose another tune. And yeah, it's about 50 lines of code. It's fairly straightforward. And it's sort of composed quite nicely of these little independent components, as you've kind of seen, hopefully. Well, I could show it, possibly. Let's see, shall we? So I have this thing. I go to, okay, oh no, how about I actually stop sharing? and show you the device. How does this work? I should have done this, put the USB camera on. This is not great. Okay, right, I'm going to plug it in. This probably won't work. Oh, it's making it, it's got a light. Okay. So unfortunately I can't do the screen share at the same time as, maybe I'll show you what I'm doing on the screen and then okay, so this is what I'm going to do. I'm actually in the so can you see my screen here? I'm hoping you can. My terminal.
Yes, we do.
Yeah, we
Cool.
can see your screen.
Okay, so I'm actually in the directory with the code. You know, this is the actual code, and you can see like this is the you know, the actual playing stuff. There's the play thing we just saw. So we're actually going to bootstrap it. So then we run TinyGo flash. So TinyGo, and basically we're saying we're targeting the itsy bitsy M4, and it's quite nice because it will actually talk directly. It'll find the itsy bitsy M4, it'll find the serial device, and it will actually flash the current program in the current directory. Dot is the current package, and it will send it to the thing, and then we're going to you know, say echo flashed, and then we're going to wait a little while, and then we're going to actually talk to it via the serial device, which is available on that USB device, so we can actually see it outputting something, which is very, very, very useful for debugging. There's actually a sleep at the beginning of the program, so that we should see most of what it does. Let's see whether this works, shall we? No. Oh, I should. Oh, it's flashed. Oh, okay. Now it's waiting for a button, and I can show you. Okay, so let's me stop sharing. Okay, now we have this. Okay, moment of truth. So I press a button. Ding, dong. Oh, I pressed it too long. Now it's actually playing a tune. I haven't got as far as actually doing. Oh, I pressed another tune. This is another. That was the start of Happy Birthday, I think. Oh, that was another tune. Okay, so usually it would just go ding dong, ding dong, ding dong, and then if I do a long button, then it starts playing a tune, random tune. So this would be making a noise if it was actually connected up. When I said making a musical doorbell, I was totally lying because it doesn't actually work yet. But there you go. Sort of, you know, it sort of works. So that's basically that. Let me start sharing my screen again. There were a number of challenges involved here. I actually had very little, no background in doing any of this sort of low-level hardware type stuff, really. So you know, this microprocessor stuff. There's a lot of terminology out there and assumptions that people kind of assume that you'll know because obviously you're doing this stuff, so you're immersed in this stuff, and I wasn't. So like for example, oh yeah, well of course, you know, you can use all these pins as GPIO pins even if they're not marked as GPIO pins, or you know, what these names mean. You know, there are all these, there's loads of names for microprocessors, and there's just loads of stuff that you don't necessarily, that's not obviously stated. USB connection was a bit flaky for me, so every so often I'd have to unplug it or plug it in or reboot the whole machine, but that's probably just Ubuntu. And yeah, there are lots. I mean, TinyGo supports loads of processors, but they're not always explicitly listed. There are hundreds of processors around, and actually they often differ only in relatively minor amounts. It'd be quite nice to have, I don't know how it would work. And another annoying thing from my point of view is I couldn't use GoDoc because if you're a TinyGo package, you have to import the machine package, and that's not in the standard library, and the Go documentation command just fails because it can't read the machine it can't because of that, which is a bit annoying. There are probably lots of things I haven't talked about, I haven't remembered. It was a fun process though. And yeah, what we actually want to get it to do, well, of course, actually hooking it up and actually get it functioning as a doorbell would be quite nice. But it's been fun. And the other another important thing here is to translate from some other file format like MIDI or ABC tune format. There are loads of tunes in ABC, which is kind of ASCII-based tune format. Something to translate from that to this very simple format that I've got going, and I think that shouldn't be too much work, but needs to be done. It'd be nice to be able to store the tunes on the flash drive rather than having to recompile the program. It would be really cool to have some secret functionality that you could get by pressing the doorbell in a particular way, or two of you pressing. I don't know. I'm open to ideas. There would be lots of possibilities. So overall, fun project. So maybe I'll do an update in a while if it actually starts working. Thank you very much.